Hi student, welcome to my channel Education Shop. In this video solve example 11.9 from the book Heat Transfer by Sinjal 6th edition. This statement is relevant about cooling hot oil by water in a multi-pass heat exchanger. This is the multi-pass heat exchanger. The number of tube passes is 8 and the shell is single shell. So you can say that it's a one shell and 8 tube passes heat exchanger. Hot oil is to be cooled by water in a one shell pass and 8 tube passes heat exchanger. The tubes are thin walled and are made up of copper with an internal diameters of 1.4 centimeter. The length of each tube pass in the heat exchanger is 5 meter and the overall heat transfer coefficient is 310 watt per meter square dot Kelvin. Water flows through the tubes at a rate of 0.2 kg per second and the oil through the shell at a rate of 0.3 kg per second. The water and the oil enter at the temperatures of 20 centigrade and 150 centigrade respectively. Determine the rate of heat transfer in the heat exchanger and the outlet temperature of the water and the oil. In this case, oil is taken as a hot fluid which inside temperature is 150 centigrade and its mass flow rate is 0.3 kg per second, and water is taken as a coolant and its inside temperature is 20 centigrade, not 2 centigrade. That's a mistake, and its mass flow rate is 0.2 kg per second. Let me write the data first. How many tubes are there? The number of tube is 8. The internal diameters of the tube 1.4 multiplied 10 to the power minus 2 meter. The length of the tube, that is 5 meter. Overall heat transfer coefficient, that is 310 watt per meter square dot Kelvin. Next is the mass flow rate of the cool fluid, that is water, 0.2 kg per second. Inside temperature of the cool fluid in, that is 20 centigrade. Here you can see, and the heat capacity of the cooled fluid is also constant, that is 4.18 kilojoule per kg Kelvin. Now the mass flow rate of the hot fluid, that is 0.3 kg per second. The temperature in of the hot fluid, that is 150 centigrade. The Cp value of the hot fluid is constant. It will be provided in the exam, that is 2.13 kilojoule per kg Kelvin. What are our requirements is to determine the rate of heat transfer in the heat exchanger, the outlet temperature of the hot fluid and the outlet temperature of the cool fluid. These are concerned to find. Now let's come to its solution. First we will find the heat capacity rate of both the hot fluid and cool fluid, that is equal to m dot h Cph. M dot h is 0.3 and Cph value is 2.13. Multiply with each others and you will get capacity rate of the hot fluid, that is 0.639 kilowatt per Kelvin. Capacity rate of the cool fluid, that is equal to m dot c Cpc. M dot c is 0.2 and Cpc value is 4.18. Multiply and you will get its value, that is 0.836 kilowatt per Kelvin. Here the C minimum is the hot fluid, that is equal to 0.639 kilowatt per Kelvin, and C maximum is the cool fluid capacity of the cool fluid, that is 0.836 kilowatt per Kelvin. Next we will find the capacity ratio, that is C, and it is equal to C minimum divided by C maximum, and it is equal to 0.639 divided by 0.836. Solve this on calculator and it will give you the capacity ratio C, that is equal to 0.764. Next we need to find the maximum heat transfer in the heat exchanger, that is equal to C minimum and change in the maximum temperature in the heat exchanger. What is C minimum? This is C minimum, and the maximum change in the temperatures of the heat exchanger is nothing but it is equal to T hot in minus T cooled in. Now enter the value 0.639. T hot in is 150 minus T cooled in, that is 20. Solve this on calculators and it will give you the maximum heat transfer in the heat exchanger, that is 83.1 kilowatt. Also the surface area of the pipe is equal to pi dl. This is for one single tube. There are 8 tubes, that's why you multiply with n. N is nothing, it is the number of tube passes, that is 8, and pi is constant. D value is 1.4 multiply 10 to the power minus 2 meter. Length is 5. Just multiply and you will get surface area of the tube. that is 1.76 meters square. The next important terms in order to find this requirement, to find the NTU, number of transfer unit, that is equal to surface area of the tube in a heat exchanger, overall heat transfer coefficient divided by C minimum. Surface area is 1.76, overall heat transfer coefficient is 310, C minimum 0.639. Just solve this on calculator and it will give you the value of NTU, and that is 0.639. Remember, this C minimum is in kilowatt, so we will convert that into watt per Kelvin. That's why we multiply with 10 to the power 3. When you perform this division on calculator, you will get the value of NTU, that is equal to 0.854. Now with the help of this NTU value and the capacity ratio, we can find the effectiveness of heat exchanger with the help of this graph. Here on the x-axis is the number of transfer unit is used for one shell pass and multiple of 2, 4, 6 tube passes. On the y-axis is the effectiveness of heat exchanger. This curve represents the capacity ratio C, that is equal to 0.764, and the NTU value is 0.854. With the help of these two values, we can find the effectiveness of the heat exchanger. Look at this. The NTU value 0.854 will lie here. So here 0 to 1. The mid of 0 to 1 is 0.5 and the mid of 0.5 to 1 is 0.75 and or 0.85 lie over here. This is our point. Next is to check where the capacity ratio is 0.764 lie. This curve is for the ratio 0.75, so our curve will lie above the 0.75 curve. It will be lie over here. Our NTU value is here. We will coincide this NTU value with our capacity ratio curve. So here it meets. If I move horizontally, it will intersect with this y-axis and it will almost give you the effectiveness of heat exchanger almost 0.47 or 47%. So I can say that the effectiveness of heat exchanger is equal to 47%, or in other words 0.47. And we also know that effectiveness of heat exchanger is equal to Q actual heat transfer divided by maximum possible heat transfer. The actual heat transfer we need to calculate. The Qmax we have previously calculated. Here you can see its value, that is 83.1 kilowatt. Rearrange this equation for the actual heat transfer, that is equal to Q dot max, and the effectiveness of heat exchanger, that is 83.1 kilowatt. Effectiveness of heat exchanger is 0.47. Multiply with each other and you will get the actual heat transfer in the heat exchanger, that is 39.1 kilowatt. This is our first requirement that is asked in the statement, is let's say 1. Also this actual heat transfer is equal to capacity rate of the cooled fluid, cool temperature out minus T cool temperature in. We are interested to find this term, the cool temperature out. Divide both sides with Cc, capacity rates of the cooled fluid. Shift this term to that side. I can say that T cooled is equal to T cooled in plus Q dot divided by capacity ratio. Now T cooled out is equal to, what is T cooled in? Temperature, that is 20 plus Q dot, that is 39.1, and capacity rate of the cooled fluid is 0.836. Just solve this on calculators and it will give you T cooled out, that is 66.8 centigrade. This is the second requirement that is asked in the statement. We also know that heat transfer rate is equal to capacity rates of the hot fluid, temperature of the hot fluid in minus temperature of the hot fluid out. Now we are interested in this term. Divide both sides by CH. This will cancel out with this and shift this term to that side and this term to this side. After rearranging the equations, we can say that T hot out is equal to T hot in minus Q dot divided by capacity rates of the hot fluid. And I can say that T hot out is equal to T hot in. What is the hot temperatures of the fluid is 150 minus Q dot, that is 39.1 divided by capacity rates of the hot fluid, that is 0.639. Just solve this on calculators and it will give you the hot temperature out, that is 88.8 centigrade. And this is the final requirement that is asked in the statement. I hope you understand. If still there any confusion, you can ask in the comment section. Please subscribe my channel if you haven't subscribed yet. Thank you so much.